So there are lands few and far between on Earth itself that are hospitable to humans by any measure. But survive we have. Our primitive ancestors, when they found their homes and livelihood endangered, they dared to make their way into unfamiliar territories in search of better opportunities. And as the descendants of these explorers, we have their nomadic blood coursing through our own veins. But at the same time, distracted by our bread and circuses and embroiled in the wars that we have waged on each other, it seems that we have forgotten this desire to explore. We, as a species, were evolved uniquely for Earth, on Earth, and by Earth. And so content are we with our living conditions that we have grown complacent and just too busy to notice that its resources are finite, and that our sun's life is also finite. While Mars and all the movies made in its name have reinvigorated the ethos for space travel, few of us seem to truly realize that our species' fragile constitution is woefully unprepared for long-duration journeys into space. Let us take a trek to your local national forest for a quick reality check. So just a quick show of hands here. How many of you think you would be able to survive in this lush wilderness for a few days? Well, that's a lot of you. How about a few weeks? That's a decent amount. How about a few months? That's pretty good too. So now let us imagine that this local national forest experiences an eternal winter. Same questions. How many of you think you would be able to survive for a few days? That's quite a lot. Now, how about a few weeks? So for a fun twist, let us imagine that the only source of water available is trapped as frozen blocks, miles below the surface. Soil nutrients are so minimal that no vegetation can be found. And, of course, hardly any atmosphere exists to speak of. Such examples are only a few of the many challenges we would face on a planet like Mars. So how do we steel ourselves for voyages whose destinations are so far removed from a tropical vacation? Will we continuously ship supplies from planet Earth? Build space elevators or impossible miles of transport belts that tether your planet of choice to our home planet? And how do we grow things like food that grew up on Earth, like us? But I'm getting ahead of myself. In our species' journey to find a new home under a new sun, we are, more likely than not, going to be spending much time in the journey itself. In space, on a ship, a hermetic flying can, possibly for many generations. The longest continuous amount of time that any human has spent in space is in the vicinity of 12 to 14 months. From astronauts' experiences in space, we know that spending time in a microgravity environment means bone loss, muscle atrophy, cardiovascular problems, among many other complications that range from the physiological to the psychological. And what about macrogravity, or any other variation in gravitational pull of the planet that we find ourselves on? In short, our cosmic voyages will be fraught with dangers both known and unknown. So far, we've been looking to this new piece of mechanical technology or that great next-generation robot as part of a lineup to ensure our species' safe passage in space. Wonderful as they are, I believe the time has come for us to complement these bulky electronic giants with what nature has already invented: the microbe. A single-celled organism that is itself a self-generating, self-replenishing, living machine. It requires fairly little to maintain, offers much flexibility in design, and only asks to be carried in a single plastic tube. The field of study that has enabled us to utilize the capabilities of the microbe is known as synthetic biology. It comes from molecular biology, which has given us antibiotics, vaccines, and better ways to observe the physiological nuances of the human body. Using the tools of synthetic biology, we can now edit the genes of nearly any organism, microscopic or not, with incredible speed and fidelity. Given the limitations of our man-made machines, synthetic biology will be a means for us to engineer not only our food, our fuel, and our environment, but also ourselves to compensate for our physical inadequacies, and to ensure our survival in space. To give you an example of how we can use synthetic biology for space exploration, let us return to the Mars environment. The Martian soil composition is similar to that of Hawaiian volcanic ash, with trace amounts of organic material. Let's say, hypothetically, what if Martian soil could actually support plant growth without using Earth-derived nutrients? The first question we should probably ask is, how would we make our plants cold tolerant? Because on average, the temperature on Mars is a very uninviting negative 60 degrees centigrade. The next question we should ask is, how do we make our plants drought tolerant? Considering that most of the water that forms as frost evaporates more quickly than I can say the word evaporate. Well, it turns out we've already done things like this. By borrowing genes for antifreeze protein from fish and genes for drought tolerance from other plants like rice, and then stitching them into the plants that need them, we now have plants that can tolerate most droughts and freezes. They're known on Earth as GMOs, or genetically modified organisms, and we rely on them to feed all the mouths of human civilization. Nature does stuff like this already, without our help. We have simply found more precise ways to do it. So why would we want to change the genetic makeup of plants for space? Well, to not do so would mean needing to engineer endless acres of land on an entirely new planet by releasing trillions of gallons of atmospheric gases and then constructing a giant glass dome to contain it all. It's an unrealistic engineering enterprise that quickly becomes a high-cost cargo transport mission. One of the best ways to ensure that we will have the food supplies and the air that we need is to bring with us organisms that have been engineered to adapt to new and harsh environments. In essence, using engineered organisms to help us terraform a planet both in the short and long term. These organisms can then also be engineered to make medicine or fuel. So we can use synthetic biology to bring highly engineered plants with us, but what else can we do? Well, I mentioned earlier that we as a species were evolved uniquely for planet Earth. That fact has not changed much in the last 5 minutes that you were sitting here and I was standing there. And so if we were to dump any of us on Mars right this minute, even given ample food, water, air, and a suit, we are likely to experience very unpleasant health problems from the amount of ionizing radiation that bombards the surface of planets like Mars that have little or non-existent atmosphere. Unless we plan to stay holed up underground for the duration of our stay on every new planet, we must find better ways of protecting ourselves without needing to resort to wearing a suit of armor that weighs something equal to your own body weight, or needing to hide behind a wall of lead. So let us appeal to nature for inspiration. Among the plethora of life here on Earth, there's a subset of organisms known as extremophiles, or lovers of extreme living conditions, if you'll remember from high school biology. And among these organisms is a bacterium by the name of Deinococcus radiodurans. It is known to be able to withstand cold, dehydration, vacuum, acid, and most notably, radiation. While its radiation tolerance mechanisms are known, we have yet to adapt the relevant genes to mammals. To do so is not particularly easy. There are many facets that go into its radiation tolerance, and it's not as simple as transferring one gene. But given a little bit of human ingenuity and a little bit of time, I think to do so is not very hard either. Even if we borrow just a fraction of its ability to tolerate radiation, it would be infinitely better than what we already have, which is just the melanin in our skin. Using the tools of synthetic biology, we can harness Deinococcus radiodurans' ability to thrive under otherwise very lethal doses of radiation. As difficult as it is to see, Homo sapiens, that is humans, evolves every day and still continues to evolve. Thousands of years of human evolution has not only given us humans like Tibetans, who can thrive in low oxygen conditions, but also Argentinians, who can ingest and metabolize arsenic, the chemical element that can kill the average human being. Every day, the human body evolves by accidental mutations that equally accidentally allow certain humans to persevere in dismal situations. But, and this is a big but. Such evolution requires two things that we may not always have or be able to afford, and they are death and time. In our species' struggle to find our place in the universe, we may not always have the time necessary for the natural evolution of extra functions for survival on non-Earth planets. We're living in what E.O. Wilson has termed the age of gene circumvention, during which we remedy our genetic defects like cystic fibrosis or muscular dystrophy with temporary external supplements. But with every passing day, we approach the age of volitional evolution, a time during which we as a species will have the capacity to decide for ourselves our own genetic destiny. Augmenting the human body with new abilities is no longer a question of how, but of when. Using synthetic biology to change the genetic makeup of any living organisms, especially our own, is not without its moral and ethical quandaries. Will engineering ourselves make us less human? But then again, what is humanity but star stuff that happens to be conscious? Where should human genius direct itself? Surely it is a bit of a waste to simply sit back and marvel at it. How do we use our knowledge to protect ourselves from the external dangers, and then protect ourselves from ourselves? I pose these questions not to engender the fear of science, but to bring to light the many possibilities that science has afforded and continues to afford us. We must coalesce as humans to discuss and embrace the solutions, not only with caution, but also with courage. Mars is a destination, but it will not be our last. Our true final frontier is the line we must cross in deciding what we can and should make of our species' improbable intelligence. Space is cold, brutal, and unforgiving. Our path to the stars will be rife with trials that will bring us to question not only who we are, but where we will be going. The answers will lie in our choice to use or abandon the technology that we have gleaned from life itself, and it will define us for the remainder of our term in this universe. Thank you.